A lot of people I know, when they talk about physics and when they think about their physics classes back when they were in college, uh, the one kind of problem that always seems to come to mind, for whatever reason, always seems to be inclined planes. And it's really just a small part of physics and what you do in this class. But for some reason, this seems to be, kind of the specific problem that always seems to stick with people. So the basic problem is we have a block, and it's sitting on a plane, and the plane makes some angle theta with the horizontal, and we want to find what's the acceleration of the block down the plane. Okay, and so if we do that, we'll look at the forces on the block. So we know that we have gravity going down. We know that we have a normal force perpendicular to the plane and perpendicular to where the block meets the plane. We know that we have a frictional force. It can be static or kinetic depending on whether or not it's big enough to overcome, whether or not gravity is bigger enough to overcome the frictional force. And that's it, right? I mean, we can also add air resistance in here. But for most of the problems that we work in this class, it's negligible anyway, and so it's best to leave air resistance out of it. And so now we want to write the net force just like we always do. So the net force is equal to ma. And so now, how do we want to start writing this? Well, what we want to do is we want to perform a change of coordinates. Okay, typically you would think that you would set up y in this direction and x in this direction because that's what we normally do. But we find that with inclined planes, the easiest way to do it is to make the block moving in the x direction. The y direction is perpendicular to it. And the reason that we do this is because now the motion of the block is only in one dimension, right? It's only moving in the x direction. So if we draw that on here, so we can redraw it with our new x and y coordinates. Notice now gravity is going to come off at a weird angle. We still have the normal force, which is completely in the y direction now. And we have a frictional force that's in the minus x direction. Okay? So now we see that we can write this. We can say that we have a normal force in the y direction. We have a frictional force in the minus x direction. And now gravity we have to deal with. And so we have to look at the angles, right? And so we've kind of talked about how to look at angles before. So we know this angle here is theta. Well, if we go up to here, we know that this angle is 90 minus theta. Again, because we have a full triangle here, these two angles have to add up to 180 degrees. All three add up to 180. This angle we know is 90, so these two also add up to 90. So if this is theta, this is 90 minus theta, then that tells us that this angle is also theta. So we can come down here onto our diagram, and we can say that this is theta. So now we can break the gravitational force up into two components. We can say we have one component in the x direction, which is going to be mg sine theta. We have another component in the y direction, which is going to be mg cosine theta. So when we write our gravitational force, x, we have mg sine theta, and y, we have minus mg cosine theta. And this is the total net force on the object. And then we know for the acceleration, the reason that we chose these coordinates is because in the y direction we know that it's not accelerating. And so we'll just call A the acceleration in the x direction. Okay, and so that's important to note that this is the reason that we chose this coordinate system, right? We could have kept x and y like this, But then we would have the block moving in both the x and y directions, and that would be a more complicated system. We could still solve it that way, and our method would totally work. But by making this a one-dimensional motion problem, it makes it much simpler for us. Okay? And so because the y direction is 0, now we can look at the y components and say the normal force is equal to gravitational force times cosine theta. Okay? And then the frictional, and so then we know that the frictional force is mu times the normal force, which is going to be mu mg cosine of theta. And so then we can write our total force, ma. Oh, sorry, I left an m off of here, which we need, of course, not just for one, to make the units correct, but for two, because we have forces over here, obviously, so we need to have a force on that side. Oops. Okay, so now we can say that ma is equal to mg sine theta minus the frictional force, mu mg cosine theta. And cancel out the masses. So we see that our acceleration in the x direction is g sine theta minus mu cosine theta. So depending on how steep this angle is, that's going to change what the acceleration is, right? And we know that, for theta, as it gets bigger, until it's 90 degrees, bigger theta goes to, the sine function theta goes up, and the cosine of theta goes down. And so that means, this is going to be more positive. This is going to be, less negative, which means we're going to have a faster acceleration, right? Whereas if we let the angle go down, then, if the angle goes down, then sine theta goes down, cosine theta goes up, and we're going to have, a smaller acceleration. And eventually we'll reach a point when this term is going to become bigger than the first term, and in that case, we know that we'll have acceleration equal to 0. But as long as our sine theta term is bigger than mu cosine theta, then we're going to have some net acceleration down the ramp, and this is all for that. And we see that it makes sense, and it also has the correct units. We have a g here, mu is just a number, and sine theta and cosine theta are just numbers. Okay, so this is how you solve your typical inclined plane problem. And then from there, we'll have problems that can get a little bit more difficult looking at the same situation. So once again, the most important part is setting up your net force equation properly. And the only difficult part for that is making sure you label the correct angle theta. And as long as you do that, then any kind of inclined plane problem you have is going to be pretty simple to solve.